3 is just like f of 2 backwards. So I'm going to go 1, 2, f of 1. Either way, I get f of 1. Now what about, remember I said it's also equal to f of 2 times 3. Well, 2 times 3 is 6. So f of 6, we just go around the circle. 1, 2, 3, 4, 5, 6. That's also f of 1. So that's what de Moivre was saying, is they're all the same. Let's try the same kind of thing with 9, modulus 9. So we could go 2 at a time, 1, 2, 3, 4. Let's say 2 at a time 4 times should be the same as 4 at a time 2 times. According to de Moivre, there's 3 at a time, and here's 4 at a time. So let's do 4. We know that 2 at a time 4 times, that gave us 8. Now 4 at a time 2 times, here's 4 at a time, 1, 2. That also gives us F8. Now just to be clear, F1 here in mod 9 is not the same as F1 in root 5, but you know by context what I'm talking about. That's why I didn't put that. Okay, also a quick point, the epsilon 3s, you get 3 separate circuits, if you want to call it. That's what Marco likes to call them. 3 different circles, because 3 is a proportion of 9. It's a factor of 9. And so because of that, we get this breakdown, which is why we'll talk later, numbers have to be prime in order to get certain conditions met, because you don't get these beautiful patterns. But anyway, those are the same patterns. And then also I want you to notice that if you do any one of these patterns n times, you're going to end up back at 0. So let's do this one 9 times. 1, 2, 3, 4, 5, 6, 7, 8, 9. I end up back at 0 no matter what. Okay? And that's important because that's what the second equation effectively is saying. And then you add up the sum of all these, and they all add up to 0. So let's review one more time. This is saying f of a b times equals f of b a times equals f of a plus b. Now, ab, excuse me. So now you understand hopefully what that means, and that if you happen to do it n times, you're going to end up back at the unity one, and the sum of them is all 0. Those are 3 pretty basic things, but de Moivre took like 30 years to figure that out. And we have this in the last 5 minutes. It's profound, it's simple, but it's also very profound and important. So de Moivre also figured out this equation, and this is just, again, a restatement of the fact that the cosine is the real part of these solutions. You remember that I have f of a, and then I have f of a bar, which is the just directly beneath it. It's kind of the conjugate. We call that the complex conjugate. We add up the 2 conjugate numbers and we get a total, which is twice the real part. And so we just take half and we get the cosine. De Moivre figured that out. And would you guess that there's a companion to that? Anybody want to have a rough guess? It's the sine. The sine, you can think of f of a minus f of b. That's kind of like the height of the difference. And we take that height and divide it by 2. We also have to divide it by I because we're on the imaginary axis. Okay? And I promise those of you who aren't math people, it's not going to get any more complicated. I know I'm losing you, but this is important. If you can hang with me for a little longer, this is the good part. We're getting there. All right. So this gives us a quick way to write Euler's equation, which we saw in the beginning. F of a equals, I call it cosine of a. I just like to call it c of a. I like to make things short and simple and beautiful. To me, this is more beautiful. So f of a is cosine of a plus I sine of a. I love that. I think that's beautiful. The complement, which is f of a bar, is cosine of a minus I sine of a. Again, these are not a pair of numbers. This is a single number with 2 parts. That's important. Okay? So one more little piece, and that is when we look at some of these equations, we're going to find it helpful to look at something that I call x of n. X of n is just f of a plus x of a, which is f of a plus f of a bar. It's twice the cosine. You could think, well, why not just use the cosine? Well, you could, but this makes it more elegant, and I like elegance. I like things to look beautiful, so that's what we'll do, and you'll see why in a minute. Okay, so stand up, turn around, sit down. Come on, let's do it. Want to make sure we're all on board. I know that was tough. That was the worst session as far as having to deal with the mathematics. Okay, we're going to get into some of the fun stuff later, but I want you to just have patience because there's a lot more coming. God's not done. I'm not done either. And the good stuff's coming. All right, so what we're going to do now is look at some particular examples. We saw the 5 and the 9. We're going to look at the simplest example, which is mod 3, which isn't really rho in phi or 0, but it's important to know. What I want to do is construct an equilateral triangle, okay? And I want to show you I haven't drawn the lines here, but you can kind of imagine a line between f of 0, f of 1, and f of Everybody see that that's a perfect equilateral triangle. The 3 points are exactly equally spaced. That's a way to construct it. So if I could find those locations, then I could, quote unquote, construct them, okay? And what I want you to understand is I can easily make a circle around an origin. I can find a spot on there. The only thing I don't know is this location in the middle, and I want to solve for basically what I call C1, which is cosine of 1. If I've got that, I can find those other 2 points, just draw on a straight line, and I'm done. Everybody understand how that works? So all I really need is one element. So those of you who are engineers, and I know you know this, if I have one unknown, how many equations do I need? One, okay? What's my one equation? I've already given it to you. Anybody want to make a guess what my one equation is? It was one of the DeMove things. Okay, nobody got a guess? It's that the sum of the roots equals 0. Remember that one? That's important. That's what we're going to use. So F0 plus F1 plus F done equals 0. Okay? They have to because they're equally spaced around a unit circle. All right? That's my equation. Now what I want to point out is F1 plus F done, that's X1. Remember? We defined that. And FO, that's 1. But I'm going to throw that onto the other side, and I got a negative 1 over there, and I simply have X1 equals minus 1. Everybody with me? The F1 plus F done, that's X1, and the FO I put on the other side, that's negative 1. Okay? Clear? And now the cosine is half that. Remember that? So the cosine of this is negative a half. So this point here is exactly bisecting the center to the outside of the circle. And if you've ever constructed a perfect circle, that's how you do it. You just find that spot that's halfway between, and then you can construct the rest. So basically, this is the solution to the problem of constructing this figure. Now, you can add the sign, which, again, you just take a cosine squared plus sine squared equals 1, right? And hopefully we can just do a little algebra and figure out square root of 3 over 2, okay? And we're going to get the plus over here and the minus over there. They have the same imaginary part, just with the plus or minus, okay? All right, we're gonna move on to a little bit more complex, but the same process, okay? I want to do now, because I'm going to just tell you in advance, the pentagon is going to have 2 solutions. So two unknowns. So how many equations are we going to need? Come on, everybody, shout it out. 2. We're going to need 2 equations. 2 equations, 2 unknowns. Sort of suggests that we're going to have to do something in quadratics, okay? And I'm going to propose to you. I have been doing quadratics this way for 30, 40 years, a long, long time. And I don't know anybody else who does quadratics the way I do them. And I think you should do them this way. This is the best way to do it. You can literally do quadratic equations in your head if you do them this way, okay? Takes a little bit, so this is kind of an aside, but I hope you'll value this, honestly. This is good stuff. Okay, we learned, actually it was Gauss, and we're going to get to Gauss in a little bit. He determined that remember we looked at x to the n equals 1, remember that one? That had n solutions, right? Spaced around the circle. Well, Gauss said any polynomial of order n is going to have n solutions, and some of them are going to be real, some are going to be imaginary, some will be complex. Always n solutions. Sometimes they're even repeated, okay? But there's always n solutions. So a quadratic, we know, has 2 solutions. So I can say the solutions, the x is the unknown, and the x1 and x2 are the things I'm trying to find, okay? So I know that x1 and x2 are solutions. I don't know what they are yet. That's the whole point. But I know they're solutions. So I can just multiply them out, because, again, you can see if x is equal to x1, I'm going to get 0. If x is equal to x2, I'm going to get 0. Either one of those solves my equation. Is everybody with me on that? Okay, this is the way Gauss looked at it, and this is the way I like to look at it. Well, one way to do it is then say, multiply this out. X times x is x squared. And then I get the x terms, the times x terms, I'm going to get minus x1x and minus x2 times x. Well, x1 plus x2 is the sum, x1 and x2. In other words, the sum of the solutions is s for sum. Okay, yeah, you're way ahead of me. x1 times x2, they're both negative, so it becomes positive. That's the product. So all quadratic equations, let me say this again. How many quadratic equations? All quadratic equations can be written in this form. All you have to do is just make sure we're used to a squared plus b. Make sure you divide through by a, so the coefficient of the first term is always 1, and then you know that the coefficient of the second term is minus s. Don't forget the minus sign, that's important. minus the sum, and the coefficient of the third term, the unitary term, is product, or P. Okay? That's always true. And so always think of it in that way. Now here's the trick part, okay? What I do is I say the average of the solutions. I don't know the solutions yet, but I know their sum. I know the average is half the sum, right? Can you do that in your head? Usually, you know, unless it's like some really complicated number with a lot of digits, you can usually do that in your head, yeah? Okay, now here's the tricky part, and this is, you have to memorize this little formula, but I call this the radical. The radical squared, this is the part that's under the radical. Radical squared equals the average squared minus the product. Memorize this and you can do it in your head. If you can figure out the average and you know the product, you can figure out the radical, okay? And then, boom, that's your solutions. X1 and 2 is the average plus or minus the radical. Isn't that a lot easier than minus b plus or minus square root of b squared minus 4ac all over 2a? I think this is way easier, and this is how I do it. And I can oftentimes do it in my head. Not always, but a lot of times I can just do it in my head because I remember this. It's handy. I'd recommend using it. All right, now we're going to actually apply it. We're going to do the pentagon. Same thing we did with the equilateral triangle, we're going to now do with the pentagon. Okay, so there's the pentagon, and again, I have 5 points equally spaced around the unit circle. If I could find these 5 points, that's equivalent to constructing a pentagon. Everybody with me? Okay, and I know that these two are right above each other, the E1 the F1 and the F done, and the F2 and the F do, they're right above each other, so the cosines are going to, I just have basically two unknowns. The cosine 1 and cosine 2. Everybody clear on that? So I'm going to need how many equations again? 2 equations. Now this is the part. Now, remember I said we get the sum and the product? If I can get one equation that gives me the sum and another equation that gives me the product, what can I do? I can make a quadratic equation and solve that, and I'm done. Get it? Okay. And then the solutions are going to be the answers I'm looking for. So let's do that. X1, again, add them all up. X1 plus X1 is the sum of these two. X2 is the sum of these two. And then I took the F1 and put that over on the other side, so I get this equation. Everybody with me? X1 plus X2 equals minus 1. That's just the sum of all the roots equals 0. I put the 1 over on this side. Did I lose anybody? Right? Okay, that's important. So that's the sum of these products. Now I want to find the product of X1 and X2. Let's see what that looks like. What I'm going to do is take my X1 and X2 and I'm going to expand them out. X1 equals F1 plus F done. X2 equals F2 plus F do, right? And then I'm going to multiply them out. And they're real easy because the product of any two is just adding the angles, right? Or adding these indices. That's all I have to do. It's very simple. So F1 times F2 is F, that's like F3, which is F do. Did I lose anybody? F1 times F2 is, just add the angles, F3. So that's the same as F do. F1 times F do, well I'm going forward 1, and then think of it this way. When you're multiplying a positive number, you're going this way, counterclockwise. When you're multiplying a negative number, you're going this way, counterclockwise. Okay? So F1 times F do, that gets me to F done. Okay? So that's this term here. Then I have F done times F2. Let's try it. I go back 1 and then forward 2, 1, 2. That's F2. Well, wait a minute. Excuse me. Back 1 and forward 2. That's F1. Excuse me. That's this one here. So that's this term here. And then the last one is F done times F do. Minus 1, minus 2 more. That's F2. And that's this term here. Looks like I got a complete set here, and I know that the sum of all of them is 0. So these 4 are going to be minus 1. So now I know the sum is minus 1 and the product is minus 1. Everybody with me? Okay? So what do? We know the sum and the product, so we can immediately do what? Write a quadratic equation. X squared minus the sum, minus 1 is plus 1, so plus x minus the product is 1. That equals 0. And that's going to give me my two x's, the x1 and the x2. That's what I'm solving for, right? Let's do the trick. This is the part that I would normally do in my head, but I'm going to show you explicitly. I know that the average of the solutions is minus 1/2, because that's half the sum, right? And then the radical squared is that number squared, so that's 1/4, minus 1 or plus 1. So the radical squared is 5/4. Okay? And hopefully you can do that in your head, but if you can't, write it down. So 5/4 is the radical squared. So now I know the answers. I can just write them down. x1 is minus a half plus the square root of this, which is square root of 5 over 2. Square root of 5 over 2. That's starting to look like something, isn't it? That's 1 less than phi. So that's phi minus 1, which is 1 over phi. Told you phi was going to show up here. That's the first solution. That's x1, the sum of these two. Okay, and then x2, we do the same thing except do the other sign. Minus a half minus square root of 5 over 2. Well, that's just minus phi. You guys know the number phi, the special golden ratio number. That's the number. So now to get the cosines, we just divide each of those by 2. And those are the answers that we were looking for. Or we could just use the x's. Now we know exactly where to construct those. So we can find those points, and then we can find all 4 points, and we're done. Okay, so this is how you can construct a pentagon. It's the same thing. And you notice I've used the word construct quite a bit because I know what we're going to do next might seem like overwhelming. It's like, how on earth can we do this? But there's something called constructability. And I just want to point out that constructability, being able to construct something, is exactly the same as calculating the cosines. It's the same problem. It's just calculating the cosines is the arithmetic way of doing it. Constructing it is the geometric way. But they are the same freaking problem, okay? So this is important. The ancients spent much effort to find which regular polygons could be constructed with ruler and compass, okay? That's an important problem. They've been working on that one for thousands of years. In 1796, 19-year-old Carl Gauss found the answer. Anybody want to know the answer? So what we want to know is how many sides do regular polygons have that are constructible? And he said, well, that's the answer right there. That's what he figured out. 2 to the m times f of n. Now 2 to the m, that's pretty, let's just focus on that term right there. We know you can't construct a 2-agon, but you can construct a 4-agon, right, which is just a square. And that's just like those, basically those 4 points. Remember we saw 1, I, -1, and negative I. Those 4 points on the unit circle, we can do that. And we also know that we can bisect an angle. So if we can construct a square, we can construct an octagon, right? And if we can construct an octagon, we can construct a 16-agon and a 32-agon and a 64-agon and a 128-agon, okay? So that's what the 2 to the m is all about. It just means you can bisect angles. That's all it means. But the f of n, that's more interesting. We know for sure that 3 and 5 are constructible, so let's hope that 3 and 5 show up in f of n. F of n is called the Fermat number, or the of n, okay? And guess who gets credit for the Fermat number? That's what a Fermat number is, 2 to the n plus 1. Yep, you guessed it. His name is Pierre de Fermat. I love saying it in French, but English people usually say Fermat. But anyway, that's the number. He had other reasons for figuring out. He didn't take that number and say, oh, that's the number of sides. He didn't go that far with it. He had other reasons for saying that number is interesting. But do you remember way back when we talked about the +1? Are you getting an idea what this +1 is all about? It's this one special root that's sort of separate from all the others. And that's what the +1 comes from. Well, let's calculate a few of those values. If n equals 0, 2 to the n is 1. 2 to the 1 is 2 plus 1 is 3. So f of n equals 0 is 3. Let's try the next one. 2 to the 1 is 2. 2 squared is 4. 4 plus 1 is 5. So f of n when n is 1 is 5. Let's try one more. 2 to the squared is 4. And 2 to the 4th is 16. So 16 plus 1 is 17. So that's a special number as far as from apparently a 17-agon is constructible. And by the way, that is what Gauss did when he was 19. He constructed a pentagon. He was the first person in 2,000 plus years to do it. And although you might say, what on earth good is there in constructing a 17-agon? Well, I think these magic squares are very much connected with this idea, and we're going to get there, but it's a bigger deal than most people would give it credit for. It's a big deal. By the way, I have actually done 17-agons. I've constructed one, I'll show you in a minute, and I have gone to the trouble, believe it or not, I've got an Excel sheet to show you that I have constructed a 257-agon. I've calculated all the cosines, which is the same thing. I didn't do it on paper, just so you know, but I haven't done a 65,000-agon yet, but it's possible in theory, and I can show you why. And by the way, it turns out they have to be prime numbers, and if n is 5 or greater, it's no longer prime. Nobody's ever found any primes for mod numbers greater, and so they're not constructible for the same reasons that we talked about earlier, with 3 being a multiple of 9, things like that. So that's a detail we can leave for another time. I do want to spend just a little bit of time actually constructing or calculating the cosines of a heptadecagon. It's a 17-agon. Now, I promise I'm only going to do this in one slide. I'm not going to actually go through the math, but I'm going to show you the process. The process is important. So there's our 17-agon. We got 8 points on the top, we got 8 points on the bottom, and we got that one extra on the side. Okay, and there's 17 points equally spaced. They all have this, the ep1 and ep-done have the same real part, the cosine. Okay, so we really only have 8 things. We need cosine 1, cosine 2, or x1, x2. We get all those. We have 8 things that we're looking for, x1 through x8. We're going to solve it in those terms because it turns out to be, I think, more beautiful. And I care about beauty. So x of 1 is equal to ep1 plus, excuse me, x of a, all the x of a is equal to x, why did I lose my pointer here? I need to find it. Oh, I'll be darned. Well, the light's there, but it's not going anywhere. You want to take a look at it? Okay. Anyway, I just want to show that ep a plus ep day is equal to x of a. That's nothing new, and that's 2 cosine of a. You got it working. Oh, you got another one. Is that you, John? Okay. I don't want to waste too much time on it. Okay, so that's simple enough. Now, what I'm going to do next is I'm going to group things, and this is the genius that Gauss came up with, is grouping things, and we're going to group them in a weird way. The way doesn't make any sense right now, but it will make sense, I promise, later on. So the first group is x1 plus x4. So in other words, ep1, ep-done, ep4, ep-door. Those 4, that's 4 terms, okay? That's equal to the first group. We call it G1. The second group is x2 plus x8. 4 terms there. G3 is x3 plus x5. G6 is x6 plus x7. Why we grouped them in that weird way, we'll find out. But then we're going to group them again. We're going to say G1 plus G2, that's H1. That's actually 8 terms. That's half of the 16 terms. And H2 is the other half, okay? Why did we do that? Well, we're going to find out because it turns out, and this is the genius of Gauss, he figured out that, first of all, this should be obvious, H1 plus H2, that's all of the roots, right? And we know that all the roots together is 0, but we're going to take that special one and put it over on the other side, so all the other roots is equal to -1, okay? That special one, we just keep wanting to get that over on the other side, okay? Now, I'm not going to prove it to you, but I'm going to say these are the rest of the equations. It turns out that H1, which is this number right here, it's 8 terms, times H3, which is also 8 terms, that's going to give me 8 times 8, how many terms? 64 terms. How many terms have I got here around the circle? 6, well, not including that one. I got 16 left besides the special one. So where does this -4 come from? It turns out I'm going to get each of these terms exactly 4 times when I multiply those 2 together. And that's why it's equal to -4. Make sense? I don't expect you to believe me, but I can prove it to you. I'm not going to do that right now. G1, so right away we have a product and a sum. Excuse me, the sum's on top and the product. What does that remind you of? Product and a sum is, I can solve for H1 and H3, can't I? Because I have the sum and product, right? All right, now let's go on. It turns out that G1 and G2, they're 4 terms each. 4 terms times 4 terms is 16 terms. I get each one of them exactly once, and so in this case, it turns out to be exactly -1. Same thing with G3 and G6. 4 terms each, they're exactly, and when you multiply them together, you get all terms exactly once, equal to -1. The X's are 2 terms each, so I get 2 terms times 2 terms, 4 terms. It turns out to be X1 times X4 is group 3, G3, which is also 4 terms. And I get the rest of the equations here. Now, here's the beautiful part. I know the H's because I got a sum and a product. And now I have the sum of the G1 and G2 and the product of G1 and G2, so I can solve for G1, G2. I have this number, so I can get this G1, excuse me, G3, G6. I have the product of G3, G6, so I can solve for all the G's. Since I have all the G's, I can solve for the X's because I have the sum of X1, X4 and the product of X1, X4. Sum of X2, X8, product of X2, X8. Sum of X3, X5, product of X3, X5, X6, 7, same thing. Okay, so everybody see in principle that I could solve for all the X's, and that was the goal. Divided by 2, I got all the C's, and I can construct this thing. Clear? It's pretty stinking cool. It's worth taking time to learn how to do this. You get the principle, and I just want to say it's exactly the same principle to do a 257-agon. I'm going to end up with 127 quadratic equations, and I can do that in an Excel sheet. And so can you. It's not that hard. So the trick is to figure out how to get these equations. And there is a little bit of trick to it, but it's not too bad. But I'm not going to spend any more time with it because this is not what this is about. So, it's time to stand up, turn around, and sit down. Come on, let's do it. I don't care. I don't care. I want to make sure you're awake because I know this stuff is a little nerdy, and I know I'm a kind of a nerd. I hope I'm making it fun for you. But it does mean something. Again, I just want to go back to the fact, and how are we doing on time, by the way? I have no idea. It's 5 o'clock right now, and I started at 4. There's no freaking way I'm going to finish. But Marco, I'm hoping that you'll be on my side. Okay, we're not. I didn't know how long this is going to take, but it does mean something, and we're getting to, honest. I swear to you, we're getting to the good stuff. Okay, so let's move on. All right, so remember, for right now, all I want you to do is remember the groupings. Remember, we grouped 1 with 4, we grouped 2 with 8, we grouped 3 with 5, and we grouped 6 with 7. Those numbers, you're going to see them again. I promise. I promise. And that's when the light bulbs are really going to go off. Okay, so now we're going to turn our attention to something new. Right at the beginning, we talked about magic squares, and somehow they're connected with 17. Remember that? We're going to finally get there. Okay, so first of all, let's look at some magic squares. This is a 3x3 magic square, so every row is 15, every column is 15, and the 2 diagonals are 15. Okay, and the number in the center is 5. That's the average. Okay, that's kind of important to remember. That's the average. Okay, you've all seen those before. And here's the 4x4 that I showed earlier. And I just got to say something just unbelievable about this 4x4 squares. First of all the rows equal to 34. Which is why 34 was a pretty good guess. All the columns are 34, and the 2 diagonals are 34. That's 10 instances of 34. Is that all of them? Anybody see more? Okay. This is mind-blowing, honestly. If you think of the extending another copy of it to the right, then the 1, 11, 16, and 6 becomes a diagonal. Everybody clear on that? And that equals 34. The 14, 2, 3, and 15 is a diagonal, and that also equals 34. The 13, 10, 4, and 7 becomes a diagonal. That equals 34. Same thing with the diagonals going there the other way. So that gives me a total of 8 diagonals. So now I have 8 rows and columns, 8 diagonals. I got 16 things. Am I done? What else is there? Anybody? Okay. Let's take a look at this small square, 12, 1, 13, 8. Anybody want to quick add those up? That's 34. How about 1, 14, 11, and 8? 30 frickin' 4, 14, 7, 2, 11, 34, 7, 2, 12, 13. You kind of got to extend it. You see 4 that way. You pick, how many different squares can I get? I call those small squares. Every small square you pick, you're going to get 34. How many small squares are there? 16. 16 small squares. Okay, so let's start counting them up. I got 4 rows, 4 columns, 4 diagonals this way, 4 diagonals that way. That's 16 plus 16 small squares. That's what? Come on, 16 plus 16. Come on, help me out here. 32. You guys got it. Remember those kids I showed you at the beginning? They'd have figured that out. All right, 16 plus 16 is 32, but are we done? No, come on, somebody help me out. There's some more. No? All right, there's what I call great squares. 12, 14, 3, and 5. They're separated by 1. 12 plus 14 plus 3 plus 5. What did that add up to? 34. 1 plus 7 plus 10 plus 16? 34. There's 4 great squares, so now we got a total of 36 ways in which we're going to get 34. Do you think that's special? Do you think John Searle was joking when he said magic squares were important? I don't think so. You're not going to, I tell you what, you're not going to find this much coherence in a 6x6 or an 8x8 or anywhere. This is the most coherent map you're ever going to find right here. And it's important. And you got to know this one. And what I've been talking about, it may not be obvious yet, but that whole stuff that we've been doing with the 17-agon, that is related to why this is so stinking coherent. It's not unconnected. They have something to do with each other. All right, let's take a look at whoops, what happened? There's a 5x5. Again, with the odd numbers. I learned this trick, by the way, from John Searle. Can you see those numbers? They're kind of dark. I could see them great on my computer, but you probably can't see them. Can you see that this is a 1? Anyway, I learned this trick. It's real quick, so I'm going to just show you. It's not all that relevant to the talk, but it's cool. He says you take the diagonal, you start at 1 and you go diagonal. So 1, 2 would be here, but you jump up there. 3, 4 would be here, but you jump over here. You go 5. See how you go down the diagonal, and you can't hit the 1 again, so you go up. And then you go 6, 7, 8, and then 9 would be here, but it's up there, but then you go here, but that's not there, so you got to go to 10. And then you can't go to 6, so you got to go up. And then you go 11, 12, 13, 14, 15. You got to go up. 16, 17, which is over here. And then you go to 18, which turns out to be up here. 19, 20, up. 21, 22, 23, which is over here. 24, 25, up, and you're done. And then you go up to the 1, and you're back where you started. Did I go too fast? Everybody follow how that works? You should be able to construct a 5 by 5 magic square just with that simple rule. It's kind of cool. And anyway, the average is 13. So every row is going to add up to 65. Every column is 65. We get 10 ways, which is cool. It's not nearly as cool as this is, because you only get 10 ways here. Here I got 36 ways, and it's smaller. So although the odd well, I skipped a step. I want to take them all, go back. You notice when you're adding the number 34 or 65, you have to do an awful lot of arithmetic. And I like to make things simple and beautiful. That's important to me. It really is. So what I want to do is I delete or I subtract what I call the DC component. And remember the bar convention that I used? I have equal number of negative